Hello everyone, my name is Osama Omar and I'm a PhD student at University of Miami. Today I'm going to present our work regarding the durability performance of seawater concrete after 7 years of real marine exposure. Before starting with the topic, I would like to give you a simple personal motivation regarding the seawater. So back in my home country, Jordan, we have extremely limited fresh water. And because of that, the water is supplied every 2 weeks in most of the areas. So, and because of that, most of the homes, including mine, use rooftop water tank in order to collect water in between, as you can see in this image, which I took from my home's window. Meanwhile, the concrete production consumes a massive amount of fresh water. According to Shamsuddin's study in 2026, the concrete production consumes around 16% of fresh water. Also, EBAID in 2022 reported that the concrete production consumes around 18% of all industrial water use globally, just for one material. Therefore, if we can replace fresh water by seawater, we can definitely conserve our natural resources. By the way, in Jordan, I don't think that we have too much of seawater. So I guess we are limited on both sides. Anyway. So if you conduct a brief literature review regarding the durability performance of seawater concrete, you can detect a real gap, as we did here in this investigation. At the same time, the implementation of seawater in concrete has been historically limited by the corrosion problem of steel reinforcement. However, I can tell that with the implementation of FRP reinforcement, the corrosion problem is no longer of interest. But still, we need to investigate the long-term durability performance of seawater concrete. We know that the incorporation of seawater in concrete can affect various properties, starting from fresh concrete properties to hardened properties like the porosity, ending up with the durability performance, which is the aim of our study is to fill this gap, which is the how does this seawater concrete perform after 7 years of real marine exposure. So it's not a laboratory testing. So let me briefly explain about the case study. We extracted our materials from Hose River Bridge. This is the bridge, and this is the location of the test block. So FDOT implemented a replacement project for Hose River Bridge in 2017, and to include multiple composite elements. And they also included dedicated test blocks in order. The main purpose of this test block is just to be extracted and tested after defined period in order to determine the evolution of properties of two different materials. The first one is seawater concrete. So this test block is made with seawater, as well as we have FRP reinforcement, including the most conventional types, glass, basalt, and carbon fibers reinforcement, because CFRP is strand, and those two things is bars. Okay. So, and those test blocks were exposed to a real tidal fluctuations, which means that they were continuously exposed to wet and dry cycles, which is known to be one of the most aggressive concrete conditions. At the low tide, we can see this is the test block after the 7 years that we used. And here, the test block is partially dry. But here at the high tide, we can say it's submerged. Another thing about the exposure condition is that the Hose River has brackish water with salinity about 5,000 ppm, which also can introduce aggressive ions to the concrete structure that can interfere with the durability performance of this structure. Here, I would like to highlight two main things about the mixed design of the concrete. The first one is that we used 50% slag replacement level. And the main thing is that we use relatively water to binder ratio with 0.38. And most importantly, we use seawater taken from Key Biscayne Bay, located in Florida. And this table shows the chemical composition of this seawater with different ions, including chloride, magnesium, sodium, sulfates, etc. So it's just not a simple replacement. It's a replacement that will introduce aggressive ions into the concrete that will interfere with the durability of this system. Here, in this slide, we showed how we transfer from field exposure scale to a laboratory testing scale, starting with marking the lines, and then marking the cutting lines, and then performing saw cutting horizontally, vertically, and then retrieve the blocks. And after that, we extracted our two materials. The first material is seawater concrete. We sliced the blocks. Those are the extracted blocks. We sliced them here and take the cores, extracted cores, and then we expose the FRP reinforcement. So here is the a brief experimental program, the preliminary experimental program that we set, because this study is in progress. So we started with the mechanical performance verification to determine the evolution of the compressive strength values with the time. And then we focused on the internal concrete quality by running the ultrasonic pulse velocity to determine the homogeneity of the concrete material. And after that, we used the transport properties, including migration coefficient, as well as the bulk resistivity, to indirectly relate to the durability performance of the material. And after that, we also run the total chloride as well as free chloride content to determine the amount of chloride ingress as well as the binded chloride for this seawater system. Let's start with the results. First, for the compressive strength result. We have two types of cylinders. The first type is the cast-in-place cylinders exposed to the same condition as well as the test block. And we have also extracted cores. So for the cast-in-place cylinders, we have them up to 18 months, and they showed comparable performance in terms of the compressive strength value. And the error bar here that we have it is related to one standard deviation, okay? And those dots relates to the data points. Most importantly, we have the extracted cores, extracted from the test blocks themselves. So we have them after 9 months as well as 7 years. They showed comparable performance in terms of the compressive strength. And to confirm this conclusion, we conducted a Welch t-test in order to determine if there is any statistical significant difference between the two groups. And the results confirmed our results, which means that after 7 years of having seawater concrete under real marine exposure, the structural performance stays stable. For the UPV, we cured the cores in lime water up to 28 days. And the results show relatively stable or consistent value up to 28 days. And more importantly, we got more than 4,500 meters per second for the UPV, which can be classified as an excellent internal concrete quality, which confirms that after 7 years, there is no such defects inside this structure. And also for the bulk resistivity, we use the same curing conditions for the extracted cores up to 28 days. At the early age, it showed a little or a drop, not little, a drop in the bulk resistivity due to the degree of saturation. However, after 7 days, it showed that constant value up to 28 days, having around 25 kilo ohm per centimeter, which can be classified as a high resistivity to the chloride ingress. And this can be indirectly indicate about the excellent durability of this system. And we also confirmed the result of bulk resistivity with the chloride migration test. So for the chloride migration test, it showed low non-steady state migration test, and this can be correlated to bulk resistivity, where higher resistivity, the lower migration coefficient. So we can indirectly, again, indicate about the good chemical resistance of this system after 7 years of real marine exposure. So here is the chloride profile. The most important thing that I would like to highlight is the after 7 years, we have a point around about the total chloride content as well as the free chloride content after 7 years. If we compare between them, we can compute the chloride binding capacity, which can be 38% chloride binding capacity, which means that more than 1/3 of the chloride content inside this system is not available on the reaction site. It should be noted that we have the inner depths still in the process for this test, and this is the initial theoretical value with the introduced chloride content in the system, and this is after 18 months, and this is the 7-year value. The key thing here is that our durability assessment indicators consistently show that we have an durable performance of seawater concrete exposed to real marine exposure, starting from the compressive strength that showed a stable structural performance, as well as the excellent internal concrete quality, ending up with the indirect indicators using the transport properties, as well as the 38% of chloride binding capacity. Now, the main conclusion of our study is that the results show that this system is durable, exposed to real marine exposure, and also it highlights the feasibility of using seawater concrete to FRP reinforced concrete structures. However, we have two main limitations. The first one is that we have single parameters, including the one replacement level of slag, as well as the single water to binder ratio, which can limit the generalization of this study. And also, do you remember that we talked about the external water, which is a brackish water, which can underestimate the exposure to full ocean water. Finally, we used durability indicators like bulk resistivity to indirectly indicate about the chemical resistance of this system. However, they originally developed for steel reinforced concrete structure, so it may be beneficial to revisit those thresholds to be updated for FRP reinforced seawater concrete structures. Finally, I would like to acknowledge the support from FDOT as well as the Structures and Materials Lab at University of Miami. Thank you for your attention.